This is an interesting question in logistics. So A, B, C, D and E, A, B, C, D and E are in a continuous clockwise loop, that is A to B, B to C, C to D and D to E, and then E to A. The central data repository compile the boarding and deboarding statistics for a specific peak hour. However, due to a system glitch, the individual station-to-station traffic metrics was lost, leaving only the aggregate chart data and the network's strict operational constraints. So, basically there are 5 stations A, B, C, D, E. Now at A, the number of people boarding the train is 15 and deboarding is 20. At B, the number boarding is 20 and deboarding is 10. At C, the number boarding is 25 and deboarding is 15. At D, the number boarding is 10 and deboarding is 30. And at E, the number boarding is 20 and deboarding is 15. And this goes on in a loop from A to B to C to D to E and back to A. So it's like a circular kind of path. Now, due to ongoing track maintenance, no passenger is allowed to travel more than 2 stations away from their boarding point. That means if somebody boards at A, he has to get down at either B or C. If somebody boards at B, then he has to get down at C or D. Passengers can travel only in the clockwise direction. Clockwise we are meaning A to B to C to D to E and back to A, like that. They cannot go in the reverse route. The number of passengers boarding at any station who travel exactly 2 stations away is an odd number for exactly 2 of the 5 stations. The number of passengers boarding at any station who travel exactly 2 stations away is an odd number for exactly 2 of the 5 stations. We'll come to this later. The traffic volume moving directly from C to D is strictly greater than the traffic moving directly from B to D. So C to D is greater than B to D, and the number of passengers traveling from C to E is a perfect square greater than 1. So these are the constraints. Now let us try to make a chart as to how these people are moving. So basically we can see that the passengers move from A to B or A to C or B to C or B to D or C to D, C to E, D to E, D to A, E to A and E to B. These are the only movements possible. Now if we take that the passengers traveling from A to B is X, then if we look at this diagram, A to B is X, then the 15 people who boarded at A, out of those X are getting down at B, so the remaining have to get down at C. So if A to B is X, then A to C has to be 15 minus X, because from A there are 15 people boarding. Now if A to C is 15 minus X, and we can see that at C, the people deboarding at C is 15 here. Out of those 15 people, the number of passengers deboarding from A to C is 15 minus X, as we just find out. So from B to C will be 15 minus X or X. Now if from B to C there are X passengers, then the people who are boarding at B, that is 20 people. People boarding at B are 20 people. See here, people boarding at B are 20 people. So out of those 20 people who board at B, we saw that B to C is X number of people. So B to D will be 20 minus X. Like that we'll have to check the data. Let's check one more. From B to D is 20 minus X. So from C to D will be how many? From B to D is 20 minus X. Now look at D. The number of people deboarding at D is 30. Out of those 30, from B to D we got how many? From B to D we got 20 minus X. So out of the 30, the remaining that they are from C to D, that is 30 minus 20 minus X, that is 10 plus X. Like that we get all the values of passengers in terms of x. Now let us look at this 10 plus x greater than 20 minus x. Why is that 10 plus x is greater than 20 minus x? Because there is a constraint given here. Number of passengers, the traffic volume moving from C to D is greater than the traffic moving from B to D. C to D is greater than B to D. So let's look at that. C to D is 10 plus x, it is greater than B to D, which is 20 minus x. So we get 10 plus x greater than 20 minus x, or x greater than 5. So now we are told something else also, that let us see the other constraints. The number of passengers traveling from C to E is a perfect square greater than 1. C to E is a perfect square greater than 1. So let's look at the figures again. C to E is 15 minus x. It has to be a perfect square greater than 1. So if we take x now, x has to be greater than 5. If we take x as 6, then 15 minus x will be 9, which is a perfect square. And if we take x as 11, then 15 minus x will be 4, which is also a perfect square, which is the given condition. So x has to be 11 or 6, and the odd even rule x. Now we apply the odd even rule, which is the third rule here. What is that? It says that the number of passengers boarding at any station who travel exactly 2 stations away is an odd number for exactly 2 of the stations. Now let us see which are the stations that we need to consider. We have to consider the marked stations A to C, which is 15 minus x, B to D, which is 20 minus x, C to E, which is 15 minus x, D to A, which is 10 minus x, and E to B, which is also 10 minus x. Out of these, only 2 of them can be odd. So if we take the value of 11, we do not satisfy that criteria. So we take the value of x as 6. So the value of x becomes 6, and now we have to we can find out any number of answers. So the question here is, what is the total number of passengers traveling exactly 1 station away during this peak hour? Exactly 1 station away. So exactly 1 station away means that is AB equal to x, then BC, that is also x, then CD, that is 10 plus x, then DE, that is also x, and then EA, that is 10 plus x. And taking the value of x as 6, we get the number of people traveling exactly 1 station away as 20 plus 5x, or 20 plus 30, which is 50.